All right, let's start our section for today. I might postpone the break again so that we progress a little bit and then take a break. So in section 2.5, we'll talk about two other methods of proving things. So far, our proofs are usually direct. So you assume something about objects until you finally derive the statement or property that they must have, like you did on your quiz. Today we will see two different methods of proving, a little different techniques, just different organization of the proof. And they are called proofs by contradiction and then contraposition. Particularly these two methods are very, very similar, just organization is slightly different, but basically one can say that they're almost the same thing, but there are also differences. So one by one. So first we'll illustrate them with a few absolutely trivial proofs, just so that we can illustrate methodology, and then we'll analyze two historically famous mathematical proofs that use this methodology. And I assume that very often you saw this methodology in your math classes because we use it all the time. So, proof by contradiction works the following way. Let me write the structure here. So you want to prove a statement, let me call it P. And then you work the following way. Instead of proving P, you prove the following, that the negation of P leads to contradiction. And then it gives you the right to conclude that what? That your statement P is correct. Does this make sense first to you, yes or no? Because one of them should be true, and then if you deny not P because it led to contradiction, then P itself must be true. But as I said, some branches in mathematical philosophy deny this as a valid way of proving things, but we do it all the time in mathematics. And that's it. So generally, whenever you use this method, you actually go from the following. You recognize who's your P, and I will illustrate it in this example from the notes. It says, there is no integer which is both even and odd. So that will be my P, that I want to prove this P. But instead of proving P, what will I assume? The opposite, negation of P. So assume not P, which would be what? That there is such integer. Here it says there is no such integer. You will assume the opposite. There is such an integer. Such means what? Such stands for being what? At the same time, even and odd. So could it be more than one? Yes or no? So what you are assuming actually that there exists an integer n. Integer, everything is domain integers. So I don't need to write. There exists n such that even of n and at the same time odd of n. And from here I need to derive contradiction, something that just cannot happen, something that's contradictory. And how do we do that? We just interpret what this means and then use our mathematical knowledge to connect things and then get the conclusion. So what do we say here? If this statement is true, it must have a witness. Do you agree? Could it have more than one witness? Could this statement have more than one? Yes, but one must exist. Let me give it a name to it. Let C be one such number. Usually I like C for witnesses, such number. Or you can say M0 to emphasize that it is an integer. So what do I know about that witness? I know this. I know that C is what? Even. And what else do I know about that witness? That witness is what? Odd. And very often when we write proofs, we write lines like when you write computer program. So what does it mean now that C is even? Do we know by definition what that means? That N is what? That C is what? 2K for some K in Z. Line number 4. But also C is what? 2K plus 1 for some K in Z. Do you agree with my writing, or I made a little typical error? 2L plus 1. Everybody aware of that? Because being odd, that oddity might be for different witness. Because on next line, I will compare those. So immediately, it will be that I said that that's the same one. So witness for even and odd might be different. And you cannot assume for any reason that's the same. Yes?
But you were saying that it is one integer. It is the same integer that is both even and odd. So
That's
not one, still not okay for that? 'Cause it is
no,
the
it's
same
not.
integer.
No, C, that's why I call it C all the time. So left side is the same, but the definition says C is even. It has a witness. Do you agree? Give it a name. I'll call it K or however you want. Now, when it's odd, the same C, I don't see any reason to see that it must be the same witness. That's what it is. C is the same, but witness might not be. Or I have a reason to write it K if you convince me somehow. I'm just applying definition. Being odd means you have a witness. Since already witness name was taken on a previous line, I have to introduce different name for new witness until I prove that they are the same. If I do, that's fine later on. What's line number 5? Do I get that 2K equals 2L plus 1, yes or no? And then on line number 6, I'll get 2 times K minus L equals 1. And this is my contradiction. So this is usually, which is contradiction, and usually that's how I write a symbol for contradiction. 2 opposite roads hit each other. Why is this a contradiction? Be careful. Some people would say, oh, it's a contradiction. Before you argue precisely, maybe you don't have a right to call it. Yes. Why do you think that this is a contradiction?
Because any integer times 2 is going to be an even number that is going to be divisible by 2, but 1 is an integer that's not divisible by 2.
Oh, how do you know that it's not divisible by 2? Well, what do you say? When you divide 1 by 2, what happens?
You get remainder 1 and not a
Oh, that's nice. I like this argument because of quotient remainder theorem. Why? Because 1 equals 2 times 0 plus 1. So what's your remainder? 1 when you divide by 2, and this says here. So we know that the remainder of 1 modulo 2 equals 1, but now we got that the remainder 1 modulo 2 is 0, and it cannot be equal. So 1 equals 0, here's your contradiction. I like that, but you just need a little more details. Yes?
Did you not have to go one more step and say that K minus L is equal to 1/2?
No, because I don't know what's 1/2. Integers have no idea what 1/2. You cannot use that as an argument. Never mention fractions within integers. But I gave you one other argument before quotient remainder. There's a different one. Yes?
Actually, I can't tell which given the kosher remainder theorem, very right hand side.
You cannot read it. Here is contradiction. I know that this is true. Do you agree? So if you write this, it tells you that when dividing by 2, I got some quotient, and how much is my remainder? 1, and that's what I wrote here. A remainder of 1 modulo 2 is 1. But what is this telling you? That you are divisible by, so this one says 1 equals 2 times K minus L plus 0. So how much is my remainder now? 0. So my remainder of 1 modulo 2 is 0. Here is your contradiction. Yes?
Can't you just say that 2 of K minus L is of the form 2 times U, which is even?
You are going in the vicious circle. Because it is even, but that's what I show. Why someone cannot be at the same time even and odd? That's the whole statement. So you are kind of exchanging one easy statement for another easy statement. Here is the argument that I would accept. If you don't want to use quotient remainder, his alternative, how you showed contradiction. Alternative, you can say the following. If k minus, so k, there are two ways. Either k minus L is greater than or equal to 1, or k minus L is less than or equal to 0. Do you agree? Every number, every integer is either 1 or above or 0 and below. Do we know that structure of integers? And then what? If this is the case, 2 times k minus L is greater than or equal to 2, so it's different from 1. And then if k minus L is less than or equal to 0, 2 times k minus L is below 0, so it's different from 1. Did I prove in all or both cases that that product cannot be 1? So here it is, that product, it cannot be 1, and I'm saying here that it is 1, so here's your contradiction. So I proved that that product cannot be 1, and this line tells me that that product is 1, so that's a contradiction. So that's another way. Yeah, I exhausted 2 possible cases, yes.
I don't really understand how you have 2 remainders for one module.
Here? Because, let me write this once again. Let me erase what's there. Let me erase this. Are we all okay with the line number 6, yes or no? Line number 7 says that 1 equals 2 times k minus L plus 0. Is that the same thing as line number 6? So what is that telling you? This tells you that the remainder of 1 modulo 2 is 0. Do you agree with this? That's the definition of remainder. If you have, when you divide by 2, 2 times q plus a number that's between 0 and 2, that's your remainder. Do you agree with this reading or not? All right, quotient remainder says the following. So quotient remainder says the following. Every number n equals 2 times q plus r, where r is less than 2 and greater or equals to 0. Do you agree with this theorem from last time? So, as soon as I can write my number as 2 times something, and r that's greater or equal to 0 and less than 2, I can recognize that number as a remainder. So, since I got that this is 2 times k minus L, can I write plus 0? Is that okay? So does this qualify in this description, yes or no? I have 2, I have integer, and I have 0. So this is my remainder. So my remainder is 0.
Oh, okay, and you have 2.
Now, on 8, so this is from the proof. But I know my general knowledge says, wait a minute, y equals 2 times 0 plus 1. Does this also fit this description, yes or no? But this one then says that my remainder is 1. Here's a contradiction. You have 2 remainders, and that cannot. So, for example, so always when you reach contradiction or something, you can call your theorems that you know to justify either your direct proof or contradiction. Yes?
Are we allowed to use powers when using proofs with integers?
Powers, whatever standard knowledge of powers. Depends what you want to call. For example, tell me a statement that you would like to use.
Well, I was going to try to prove that a variable to a negative power equals a whole number.
Oh, negative powers, I wouldn't do that because negative powers on integers might give you fractions. That's the trouble. No, integers do not know negative powers, not fractional. They only know power 0 and higher. All right, so what happened here? One way or the other, this is now my contradiction. So what's my conclusion then? The assumption not P, that there is such integer, caused a contradiction. So what can I conclude? That my original statement is correct. So this is considered as a legitimate mathematical proof. So you start from negation of your statement. If you derive contradiction, your original statement is considered proved. So that's one of those simple ones. Basically, there was nothing. It was just how do you really main up? Everything was very easy, just opening the statement until we came here. So question is, how do you deny something that you obviously know is true up to basic statements? And that's what we did, either using quotient remainder, or as I said, knowing the ordering of numbers. That's how we show that this cannot happen. All right, just one comment. I'm not going to write the proof, we'll take a break, but just to make it sure that you understand the difference, we already talked about it. It says every integer is even or odd. Do you understand the difference between this statement and the first one? First one says no one can be both, but this one says, oh, no one can fail both. So that means, could we find one integer, you try to make it even, doesn't work. You may try to make it odd, doesn't work. Can you do it that way? Why not? I cannot do argument by contradiction, but basically I can do direct argument. So usually people say, don't do argument by contradiction if you can do the direct one. Direct one is always nicer. So generally, how would you prove that every integer is even, either even or odd?
Take the integers or make them independent and assume that it's either even.
Modulo is the easiest one. So, and I don't need contradiction on this one. I would rather go with direct, even in the notes, maybe I wrote contradiction just to practice. But generally what? Take any number n. So this is direct proof. So example 252. Take let m be arbitrary number, another arbitrary number. Then m equals 2q plus r. Is that what quotient remainder tells us? And r is what? Where r is less than 2 and greater or equals 0. So what? R is 0 or what? R is 1. Is there any third choice? No, because numbers integers between 0 and 2, less than 2 and greater or equals 0 are just 0 and 1. And then what? If you get a remainder 0, what are you, even or odd? Even. If you get remainder 1, what are you? Are we done? Done. With the direct proof, no need to do any, I don't know how.
Would you just stop it at saying that the remainder is 0 and the remainder is 1?
Yeah, because that's what it is. So you can say the following. When r equals 0, then m equals 2q plus 0, which is 2q. By definition, q is your witness. If r equals 1, that m equals 2q plus 1, and that means you are odd, q is your witness. By the way, did you notice that I used the same q here and here? Why? Because there are alternatives. They can never happen in the same line, so it doesn't force any wrong conclusion. So I didn't need. But whenever you're not sure, just call it q bar or q1. It's safer, not to assume that. Although, as I said, since there were alternatives, they don't face each other, so they don't make wrong conclusions. So these are a few statements, as I said, that are absolutely trivial, but they needed that understanding. How do you, at the end, reach the contradiction? Now we'll take a break. We'll continue at 2:40. After the break, we'll see two historically famous in mathematics proofs that work by contradiction, where construction is a little less trivial than this one, but it's not a big deal again. So 2:40 is when we continue.